All right, thanks everyone. I'm Juan Carlos Ortiz this time, not Adriana, for the ones that were in my first talk. I'd like to acknowledge the traditional owners of the land and sea country where we are and where we have worked and continue to work, recognize the elders, past, present, and emerging, and recognize that they are the original scientists of the land and sea country where we are. I'll be quick on where I come from because I already did one, so all I say is night diving is the second reason why I got into reefs. You go diving in the reef at night, it's a different space. You get to see the personality of the corals. They actually do things. They come out and back, and you see all the diversity that they are supposed to host that you don't see during the day. So yeah, that's when the real reef for me comes out. Before I go, I was going to mention something to Andrew. I won't take your point about the permits in Spanish because I have had whole conversations with you in Spanish, so I'm sure you can deal with those permits in Spanish easily. So today, we are going to be talking about the work that has been done through a big team, and it's been led by myself, Mariana, Isabella, and Karen, together with a whole lot of people that have helped us. I got the final results that I'm presenting yesterday at 9 p.m. because I really wanted to try to show a summary of the last 3 years, which is the whole thermal growth core project that we had in EcoRRAP. So it's a bit crude, but every bit of data is there at least. So you'll see where that goes. Now, when we talk about thermal performance and how well individuals perform in different conditions on a gradient, in this case of temperature, you can think of it as there is a temperature where you do best, you really like, there is a temperature that is too hot, and then you don't do very well, and there is a temperature that is too cold, and then you don't do very well as well. And in general, for many organisms, we know that those distributions tend to be tilted towards the right, so the negative effect of heat tend to be faster acting than the negative effects of cold, so that's why you have a different slope. That's what is expected. However, for corals, we didn't have a lot of information of what the growth temperature relationship was for the Great Barrier Reef, and particularly for the gradients around the Great Barrier Reef north to south, etc. And the reason why this is quite critical is because the way the corals perform over the whole year is quite dependent on the temperatures that you experience during that year. So if you think about the red bit that I have there that I call it yearly temperature range, you can imagine that is a year, right, in a particular environment. And if a coral has that particular distribution of performance, the growth of that coral would be the sum of the bars that are covered by that year, right? So if there happens to be a coral that has an optimum that is higher than that particular year or the year where they are, and the temperature starts to warm up, you will see how that particular coral is actually growing faster every year as temperature goes up. But there is a point around here where part of the year starts to be bad. And if you keep going, then it starts to grow slower than what it was before. So where that optimum is for different species in different parts of the reef is critical to know how they are going to do in the future, particularly in the recovery periods between thermal stress events, which is a lot of what we care about. So that's why we identified this as being so important, and that's why we invested quite a bit of resources on trying to get as much information as we could on the growth temperature curves for the gradients of the GBR. When I started proposing this work, even before RRAP was there, I had 2 deck applications that also said, this is amazing, you're never going to be able to do it because it's too hard. So great idea, find something else to do. But then I went to Ames. When I was with those ECRAs, I didn't have CSIM to be put as part of the proposal. I came to Ames. I looked at CSIM, and the first day I walked into Ames and they took me to CSIM, I could say, this is the place where we can do this. And sure enough, we were lucky that we managed to get a setup that would allow us over 3 years to test this over many species, well, multiple species and multiple reefs. And to give you a scope of the magnitude, this has been defined as the hardest temperature-related experiment done at CSIM so far. Ames, the current CSIM, because it's been expanded, but the current CSIM has 8 experimental rooms for heavy experimentation. We wanted to do our experiment in a single room, so we don't have another factor to account for. to be able to do that with the 10 temperatures we had, Ames had to dismantle 3 other rooms, so we used 4 of the 8, and repipe all of that to the room where we were, so they could manage to have the 10 temperatures for all the tanks at 1 degree difference consistently throughout, while taking acidification out, or pH out, or alkalinity out, so we can maintain a reasonable range as it would be expected. So they were not very happy when I proposed it. And after we did it, then 3 more people have asked them to do the same, so they are less happy now, but they still enjoy the kind of, Lauren is here, so he knows it's good and bad. It's hard work, but then they get happy and excited. So it goes both ways. So what we knew before we did this work, there have been some attempts of look at their performance, temperature performance relation for corals, but a lot of them have been done in a short period of time, mainly with respiration or photosynthesis. And even though there have been interesting results, they are really hard to interpret in terms of growth and how to relate it to vital rates. And they go sort of into many different directions. Thinking of growth or even classification as the response variable, before we started, all we had to go by was one study in One Tree Island with 3 species of Poeciloporets that had 3 temperatures in them, and different species, different colonies in each temperature. They were left for 3 days, and then Boyan waited twice. And that produced those 3 cores. The 4th one is a combination of the others. That's all we had. So we didn't have variability across. We didn't have any more species or anything else. And when everyone knew that's what it was, and everyone said, they are all going to die. You cannot keep them at that temperature low and high for a month. It's just not going to work. So we got really stressed. And Mariana, which I think was here, together we had many nights where we said, we're going to spend all of this effort and then everything's going to die and we're just going to have a nice idea that never worked. Luckily enough, we did it over 3 years. It worked pretty much every time. And what we have now after those 3 years is a bit more. So we now have growth curves for 5 different taxa, at least 3 locations across the GBR for all of the 5, and 5 locations for 2 of them. And we managed to do it with the same colonies being represented in every temperature, so we could look at colony effects. So it worked out quite well. We can do a lot with what we've done, what we have found now. Just to give you an idea, the range of temperatures between those sites, so basically there are 5 sites, but they're really representing 3 latitudes, if you will. So the average summer temperature, winter temperature for the north is 24 and 28 for summer. In the center is 23.9 and 28 for summer, 20.3. And at Heron in the south is 22 and 26.7. Something important to see here, even though in terms of the latitudinal gradient is a somewhat similar distance between central and north and central and south, the difference in temperature is not like that. So those numbers, 0.8 is the difference in the winter temperature between central and north, and 0.3 only between central and north in summer. Between central and south is 1.9 degrees for winter and 1.6 degree for summer. So big difference there, and that shows up. So if we look a little bit at what these results show, it's a little tricky when you see all those plots like that to really look at meaningful patterns just out of all of those curves. But all of those curves had parameters that are that we can calculate that are meaningful, and the most common one that people look at is the thermal optimum. Is basically the temperature at which you have your maximum growth. And how that relates to the local temperature is something that is quite interesting, because it tells you also what may happen in the future. So let's look at those a little bit. Just for consistency, the information for Kelso, which is the one of the central ones, is already published in a paper that we have in Proceedings B. And I'm not showing the results of that paper, but because I'm showing it with the new analysis, with all of the data, the results are included in there. So the same patterns are still present in what I'm showing. That was the paper that Mariana led. So now we're going to be looking at the thermal optimum, right, for those curves in different parts. So I'll start to do pairwise comparison. So we start with Stylophora pistillata and Acropora tenuis. And what I have there is the actual optimum for the different reefs, which are in the x-axis are the different reefs from north to south. What I'm going to show in a second is what the average summer temperature is for each of those reefs. So in case of the Stylophora, the average temperature is in summer is about 28 or so, and the optimum for Stylophora was higher than what that temperature was, but not by a great deal. For the central, it was closer to that optimum, a little higher, but not too much. For the south was slightly lower, but when you look at the distances, they were quite close, so there was not a big, huge difference there, not too surprising, the pattern we were expecting. For tenuous, more or less similar in the central and north, even somewhat closer, in the south a little lower, so a bit of a difference between the south being below or above, but so close to the summer average, not that big a deal. We have Platyjara, which is the only massive one we had there, and it's more or less a similar pattern with a little bit of a difference in the central and the north, not so much in the south. But then it gets interesting because we found there are quite different thermal strategies for Posilopora verrucosa and Acropora hyacinthus, where we have actually 5 reefs through the gradient. It gets a bit more interesting because if you look at Posilopora, which now we recognize as a relatively thermally tolerant coral compared with some of the others, we'll see how their thermal optimum is significantly higher, significantly higher than that the average for summer is also significantly higher in the center than the average for summer. And in the case of hyacinthus, it's quite the opposite. It's much lower than the average for summer, both in the south and in the central, and the north and in the central. And for Posilopora, again, for the south, is even higher than the summer optimum, while for hyacinthus, it sort of flips a little bit, right? And then it becomes higher compared with the others. So what we are seeing here is the emergence of this position where a coral like verrucosa may start growing faster in the mid-term or short to short term with increases in temperatures, and I'll show that in a second. Now, the other really interesting result we had, which was surprising, was that there is this general theory that because growth is quite enzymatic and is dependent on metabolic rates, the species that have an optimum that is highest are the ones that perform or grow faster. That's the hotter is better hypothesis, and it's quite well supported in many organisms, particularly ectotherms. However, many of the corals we found tend to synchrovine thermodynamics a bit. So when you look at that, this is the relationship between maximum growth and thermal optimum, and you can see how the corals that had the lowest thermal optimum had by far the fastest maximum, the highest maximum growth. And that was consistent from the north. In no-name, we only have 2 species, but still have, so that's the second reef in the north, still have the same pattern. In Kelso, we have the pattern very, very strong, like by the book, that's central GBR. In Davis Reef, again, we have the slow-growing together and the fast-growing as the highest with the lowest optimum. However, when we go to Heron, that no longer happens. It seemed like Heron is too cold for hyacinthus to be able to keep that pattern of having a lower temperature in relation to the summer average. The benefit for that, the reason we think that happened is because by having that lower optimum, they can actually grow at about 80% or more of the maximum rate all year round. So it's one of the reasons why they are so successful and they can overcompete and grow many of the corals, but they can only beat thermodynamics by so much. There is a point where they cannot go any lower because then it's too costly metabolically, we think. Now, the other really important thing with this is following individuals. We managed to have all the colonies represented everywhere, which no one has done like that before, and we could do statistics to be able to find out how consistent the thermal optimum is and the different parameters of the curves between individuals. And I'll go quickly with this, but what was striking is that while maximum growth was very variable for all the species, thermal optimum was extremely conserved for all the species within a reef. And the individuals of every individual species had a very similar thermal optimum to about 0.1 of a degree for many of the species. And that is just the dots in those graphs, not the lines. The lines are because of the posterior distributions of the Bayesian analysis. But it's just the dots on the line. In this case, you can barely see them. Bit more variability in some others, but still those dots are really, really close to that line of 0, which is, when it's 0 is the median of the population is exactly the same as the value for every individual colony, and each dot is a colony. Same thing for Platygyra. Even with Stylophora, which behave quite messy in some of the aspects, there is one row colony, but the values for the optimum are really consistent between every reef. Verrucosa, though, was the one that had the most variability. Still not a lot, but more variability than any of the other species. So this is the end. What does this mean for RRAP altogether? There are multiple thermal performance strategies among taxa in the GBR. These strategies appear to be highly consistent among individuals of the same taxa within a reef. If this consistency is evolutionary driven, which we don't know, it may pose challenges for the thermal enhancement of populations through assisted growth flow, gene flow, what Andrew was saying before. However, experiments to determine if the observed consistency on thermal strategy is genetically driven or acquired through acclimation during early developmental stages are critical. We can't distinguish between those. Tabular acropora appears to show thermal performance strategy that circumvents thermodynamics limitations until a certain point, until it gets too cold where they can no longer do that. Thermal performance may be decoupled. So this is an important point. What we are finding here is that it is possible that thermal performance in relation to your chronic temperature may not be a great predictor of thermal tolerance to acute thermal events. And when you think about it, the selective pressures may be acting in very different time scales for that. So that's a bit provocative there. We can talk about it later, but that's what the data is starting to suggest. The other really important point, Posidoropora verrucosa could be a natural short-term winner on their continual increases in temperature, and given the fact that it's somewhat thermally tolerant already, even though I know it's a little tricky to work with, it could be a good candidate species to be considered for thermal enhancement or for assistant G-flow, given the plasticity that seems to be a bit present there as well. This relationship, so this is the other critical bit. We have already incorporated these growth curves into the ecosystem model I'll talk about at 1 o'clock later today to represent within reef variability. And we now have the ability to explore not only winners and losers in the short and long term when they interact with the environment and with demographics, but also evaluate how this will interplay with interventions that try to bring corals from one place to another. So that was the reason why we tried all of this. And with that, I say gracias, and thanks to Sim again. We wouldn't have done it without it.